Okay. So gotta check the study list just in case. Recording. It's on. Yep. Okay. So first, let's go over alkylation of amines, which is a bad method for synthesis, right? Because let's say we have this haloalkane right here, and we try to alkylate it by using NH3, right? This ammonia here will be the nucleophile that's going to attack this electrophilic carbon here and kick out the leaving group, SN2 reaction, right? That's going to give us this structure here, where the nitrogen still is attached to 3 hydrogens, and because it has 4 bonds, it will have a positive charge, right? The thing that's going to deprotonate this is actually another nitrogen of the ammonia here to neutralize it, right? Right. And then once we had created another amine, this amine here is actually going to be more nucleophilic now because of the R group. Think of this as in excess. Assume excess amount of this. We're going to attack another haloalkane with this nitrogen, kick out the bromine. It's going to over alkylate the amine, right? And we're going to keep doing that until we can't neutralize the amine anymore. So let's do that. Right? So we keep going on and on until we can't deprotonate the nitrogen anymore. There are 2 hydrogens left, so we gotta deprotonate it again. Introduced another pair of electrons, which is gonna make this nucleophilic again and attack another haloalkane here. Right? Now this is the last proton here that's gonna get deprotonated to neutralize this amine. Right? But then this pair of electrons here can attack another haloalkane and get this quaternary amine here, where this is the final answer because we can no longer neutralize this positive charged nitrogen since there are no more protons on it, no more hydrogens to deprotonate, right? So this is an over-alkylated amine. Do you guys know what reaction is preferred over this if we want to make an amine instead? Like what is a reaction that we prefer to do instead? It's a name, a reaction name. Yeah. Nitration is creating a NO2 from a benzene ring, and if we could reduce that NO2 group to NH2 by reduction, right? But if we want to create it from haloalkane, it's reductive amination. Yeah, that's the better way to form amines rather than this way here, right? So yeah, that's good. That's good that you said nitration because that's gonna segue to the next section, right? Okay. And then this right here is gonna be the first part of the Hoffman elimination mechanism. And we're going to get to that later. But this whole thing here is the first part of the Hoffman elimination reaction. Yeah. And this could be an explanation question, like why this method is not preferred to do amination. It's because it will over-alkylate into the quaternary amine, which we don't want. Okay. Yeah, this whole over-alkylation thing is the first part of Hoffman elimination. And then the second part is when we bring in the silver oxide, the Ag2O. But we'll go over that reaction as we move on the study list. Yeah. Okay. Ready? Ready? Okay. Okay, so the next thing is going to be um, reduction reactions. Right, we could reduce a nitro group from a benzene ring to make this amine here, aniline. And there are two reagents, reducing reagents, that could convert this nitro group into this aniline here. Do you guys remember the two reducing agents that could do this? H2PDC is one, right? H2PDC. Or it's, wait, so Jones is an oxidizing agent. We want to use a reducing agent. I'll give you a hint. Yeah, yeah, the zinc one. Zinc, mercury, um, and then HCl. Clemenson reduction. Right, you could use either or. Let's say we have a nitrile like this. We could reduce that nitrile into this amine right here. And there are two reducing reagents that could happen as well. Right? And also make sure that when you reduce this, maintain that carbon of the nitrile right there. Right? It's not going to be this. A lot of people put this as the answer. Right? Because this is missing a carbon. Here we have 1, 2, 3 carbons. When we reduce it, we have to maintain that 1, 2, 3 carbon right there. Don't put this because this only has 2 carbons. Maintain that nitrile carbon right there. The two reducing agents that would do that is H2PDC and H2 and some kind of catalyst. Yeah, you can also use lithium aluminum hydroxide, lithium aluminum hydride, LiAlH4, and then second step, H3O plus acid workup. Yeah, you can also do that as well. Right. Brenny, nickel, or PtO2, or H2, PDC. Right. Those are the reducing agents that will reduce that nitrile into the amine right there. Okay. Now, do you guys know how we could, let's say, reduce a functional group that will like not that include that carbon right there of the functional group? Let's say we have something like this. This is gonna be nitrile right here. The other one is gonna be azide, right? Which is gonna be an N3, like that. You could reduce this with lithium aluminum hydride, second step acid workup, or H2 PDC, right? That would convert that azide into the amine right there. And we don't have to worry about the carbon of the functional group because this azide N3 here has no carbon at all, right? That whole N3 will just get reduced down to NH2 right there. Right. Okay, so that's the reduction stuff. We could reduce a nitrile group into an amine group. You could reduce a nitrile into amine, or you could reduce an azide to amine here. This is useful for synthesis because let's say we have something like this. This is going to be two-step synthesis here, right? Two-step synthesis. What do you guys think the steps are if we want to convert this haloalkane into that amine? Yeah, and why do we want to use CN over the azide? Yeah, because it adds an extra carbon here, right? This extra carbon is going to come from the NaCN, which will create this nitrile, and then we can reduce that nitrile using H2PDC, like that. Right? It's not going to be N3, right? Because we want the extra carbon here, right? Okay. So next thing, Gabriel synthesis. Right. Mhm. Yeah. So this next reaction here, Gabriel synthesis, will be connected to the amino acid chapter. Okay. So this one's gonna be Gabriel synthesis. So when you see a structure like this, phthalic amide, oh wait, hold on. Actually, uh, yeah. Let's first start with the carboxylic acid instead first. Right. We can convert this to the phthalic amide by NH3 and heat, right? NH3 and heat would convert this phthalic acid into the phthalimide here, right? And then from here, let's say that we want to create some kind of amine. How can we deprotonate this hydrogen here? What's the common base that we use? Yeah, K2CO3 as the first step. K2CO3 will deprotonate that phthalic amide into a negative charge here. And this is where you could select what kind of amine you want. Like, let's say you want like a ethyl group on the amine, then what you gotta do is just put that ethyl group on the halocane right there, right? Because what this is gonna do is just attack that carbon, kick out the bromine, and then give us this structure here. Right. Now, once we have this amide with the R group that we want for the amine, how can we get the amine now? How can we split this open into the carboxylic acid? Yeah, right. Hydrolysis. Midterm one material. We have two amides here. We could convert that into carboxylic acid and amine by H2SO4, H2O, and heat, which will create our desired amine we want and this side product here. Right. And all we did here was we made a cut between the carbonyl, carbon and the amine there, which this part is the amine part, and then that part is the carboxylic acid part right there. Right. So that's Gabriel synthesis. Okay. So the next thing is Hoffman rearrangement, where the mechanism is going to be a note card thing. So I'm not going to go over the mechanism because that's going to be on the note card. I'm just going to go over like the reaction, how to predict it, and use it for synthesis. Right. Okay. Good. Yeah. Okay. Now let's say we have Hoffman. Yeah, K2CO3 will deprotonate the amide, the phthalic amide there.
Only for amide?
You could use any other base as well, like a weak base like T, pyridine.
Can we use K2CO3 for others?
Mm. It depends on the thing,
Oh.
right? Because that's relatively a weak base, but that's a strong enough acid to get deprotonated by that weak base. Okay. That's just the common thing for Gabriel synthesis.
Amides are very unreactive.
They are unreactive, that's right, and also the hydrogen on the amide is acidic, right? Where a base like K2CO3 can deprotonate that acidic hydrogen and give that nitrogen a negative charge. Yeah. Uh-huh. Yeah. Uh-huh. Hoffman rearrangement. So this is actually from midterm one material. Do you guys know what the reactant is for this reaction from midterm one? It's gonna be a some kind of primary amide, right? And then if you have something like Br2, NaOH, and water, does this ring a bell? Like what this does to this amide here? Right?
That carbon.
Yeah, it converts this whole amide into
Continuous.
an amine here, right? Where it removes that whole carbonyl carbon as well. It gets rid of a carbon. It cleaves a carbon.
Is it amide or
Yeah, this is gonna be a amide,
looks about?
primary amide, because we want two hydrogens there. This is gonna be an amine, right? And
Primary amide.
for Hoffman rearrangement, yes, always, yeah. And this right here will cleave the carbonyl carbon, right? Because that carbonyl carbon is no longer in the product side. It's gone, right? So in synthesis, if you see one less carbon, think of this reaction here, Hoffman rearrangement. Yeah. So let's give an example problem for the synthesis. Let's say um, we have something like this.
For us.
Okay. So this is also a good review for midterm one. We see that in the reactant we have one, two, three carbons, but in the product, this side we're gonna have two carbons. We got rid of one carbon, so we're gonna think of Hoffman rearrangement, right? How can we convert this primary alcohol into a primary amide, right? So this is midterm one reactions now. Um, how can we create an amide, carboxylic acid derivative? So a hint for that is think about the most reactive derivative. What is the most reactive carboxylic acid derivative? Right. So esters is gonna be lower reactive derivative. Like there's a whole like list of them. The options are acyl-halide, anhydride, carboxylic acids, esters, amides, nitriles. Which one of those is the most reactive? Anhydride is the second most reactive, right? The higher reactive one is the acyl-halide, right? This one here. The most reactive is this acyl-halide, where X could be chlorine or bromine, right? But first, we want to create a carboxylic acid. How can we create a carboxylic acid from this primary alcohol? Jones, right? 118A. When we do Jones, we could get this carboxylic acid here. Yeah.
So in this one, we use like a less powerful one other than Jones.
Right. If we use PCC, what would that make instead?
Aldehyde.
Aldehyde, right? Because we have a primary alcohol. If we use a weak oxidizing agent, PCC, it would become an
Like
aldehyde.
the
Copper, NaOH. Oh, like copper, lithium, like the R2, Gilman. That is going to be organometallic reagent, which is the base, and that's going to deprotonate the alcohol, right? Organometallics usually react with carbonyls. There's no carbonyl here. Like Grignards, like RMGBr, RLI, R2CuLi, those are bases, which will deprotonate the alcohol instead, right? So, do you guys remember the weird reagent that can convert a carboxylic acid to any acyl halide? There's two. There's two different. One would create the acyl chloride. One would create the acyl bromide. Yeah, SOCO2. Right. SOCO2 would create that acyl chloride. What would create the Br if you want the acyl bromide? PBr3. But I see SOCO2 more commonly, so let's use that. Right. And then how can we create a primary amide now from this acyl halide? Like what kind of reagent do we want to use if we want to create a primary amide here? Right. Think about the leaving group of this carbonyl, and then we want to create this primary amide here, right? We're just gonna use this exact same structure here and add an extra proton, NH3, and we're gonna put excess ammonia, right? We'll substitute this whole halide into that amine right there, right? And now from this primary amide, we could do this reaction that we just learned about, Hoffman rearrangement. Yeah.
You cannot directly go
Uh-huh.
from this to this.
Oh, so this one here, you have to have heat included as well. Heat,
Can we get this?
It's not going to be high yield because the amine there is going to deprotein the carboxylic acid, right? So it's best to go to the acyl halide first, like the most reactive derivative, and then make any of the lower reactive derivatives. Yeah, yeah, and that's the last step right there. Nice, yeah, right. So we could do Br2, NaOH, water. That's gonna create NH2, right? But now we have the 1,2 carbon chain that we want over here. How can we create a carbonyl on the nitrogen here, right? This is what functional group is this product here? What is this functional group? Amide, right? And then to form amides, we could form it from amines and acyl halides, right? So let's make a cut here, and let's say that this part here was the amine part, and then the right part here is going to be the acyl halide part right there, right? So this is very similar to this right here, but this reactant is the acyl halide. The thing on the arrow is the amine. That creates an amide right there, right? This amine is on the reactant now, and then the thing on the arrow is the acyl halide. That also creates an amide right there. Yeah, this Br2NaOH H2O is this Hoffman rearranging reaction that we went over, where we have the amine and then gets rid of that carbon as well, right? It doesn't reduce it; it completely cleaves off the carbon of the amide to create the amine right there. That's how we got one less carbon, right? Um, the mechanism is more of a note card thing, but that's what it does. Like that reaction, that, um, gets rid of the carbon. Yeah. Uh-huh. Oh, right. So if you use lithium aluminum hydride, right, we would get this here. 1, 2, 3. We still maintain that carbonyl carbon. It doesn't get cleaved, but we want to cleave that carbonyl carbon as well, right? So we can't do lithium aluminum hydride here because that keeps that carbon, but we don't want that carbon there. Yeah, we want to get rid of that carbon, which is the Hoffman rearrangement reaction. Oh, yeah. So that was the next reaction that you talked about, right? Yeah, the thing that you talked about, the lithium aluminum hydride, that was the next thing. So I don't think we got to go over that because like, do you guys understand like how we got from here to here? We just reduced it with lithium aluminum hydride. Yeah, that was the next thing. Yeah, yeah. Uh-huh. Reduction of amide. I could go over it real quickly, more clearly. Yeah, here. Yeah, it's good. Yeah. Uh-huh. Uh-huh. So, reduction of amide. Right. Whenever you see a reducing agent like lithium aluminum hydride, always think of a hydride ion, H minus, right? That H minus is going to attack that carbonyl carbon, and then so the mechanism for the amide is actually weird here. But what this reaction will do is find the carbonyl and then cleave it off, like it's no longer there, right? That would reduce that amide into the amine right there, and it maintains the carbonyl carbon, right? That carbonyl carbon here is still there. It's not like the Hoffman rearrangement reaction where we cleave that off. It stays there. What the heck?
that could also be H2SO4, or they're the same thing?
Yeah, it could be H2SO4, it could be H3PO4, it could be any acid proton source. Yeah, it could be water as well. I've seen water as well. Yeah. So, okay, reductive amination. Yeah, okay. So for reductive amination, the reactants here are going to be an aldehyde or a ketone plus an iminium ion, and then that's going to create, let's see, no, 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 no. Wait, hold on. That's going to react with amine. And then under a pH of around 3 to 5, that's going to create the iminium ion. And then from this iminium ion, we could use NaBH3. So, wait, Na, something with the CN, BH4CN? Or is it BH3CN? Oh, BH4CN, okay. NaBH4CN, that would create an BH3, BH3CN, BH3. Yeah. Oh yeah, yeah. The original one, NaBH4, is the one that we're used to, but this is a weaker one, a weaker reducing agent than NaBH4. Right. So let's make that note.
Ryan, you're gonna post this on YouTube, right?
Yeah, I will. I will. Then NaBH4. Right. And then now let's go over the whole example. Let's say we have this ketone, and we react it with, let's say, this amine. If we put it under like pH 4, which means that we are in acidic conditions. This is a, sorry, 118B reaction here. What do you guys think is going to happen between a carbonyl, amine, and acidic conditions? Yeah, we're going to protonate the carbonyl oxygen here, and then this amine here will attack the carbonyl, and then create the iminium ion, right?
Since like
Uh-huh.
it's in acidic conditions,
Yeah.
NH2 get overprotonated.
Oh, right. So it will get protonated, right? Like, let's say it does get protonated, and then the carbonyl oxygen here can get protonated by that right there, right? Um, Let me just go over the whole mechanism here from scratch. Right. Right. That's how Nasiri does it, but the way Helix does it, right? He just directly protonates the oxygen right away. But like the Nasiri way is like you protonate this first, and then wait, did you have Helix or I mean Nasiri for 118A or oh yeah, you guys have Nasiri for 118A. So protonate this carbonyl oxygen. That's gonna create your activated carbonyl carbon, which is now a strong electrophile. We could use this amine to attack that. Pop that up there. Get the OH here and H plus. Should we just skip the mechanism? Because I don't think Helix will test the mechanism for that. I'll just teach you guys how to like predict the product, how to combine them. Yeah. Let's skip the mechanism. He's not gonna test it. Yeah, more for predictive products. Yeah, this is more of a 118B mechanism. Yeah. Okay. Okay. So first, locate the carbonyl carbon, which is this carbon right there, and I'm gonna say that carbon is this carbon right here. The double bond stays there. substitute the oxygen with the nitrogen here. So that's going to be that nitrogen right there now, right? And then it's still attached to its R group, and we get rid of one hydrogen. Right? One hydrogen leaves in the mechanism somewhere. What charge would this nitrogen have with four bonds? Plus charge. This right here is the iminium ion. Right? And then from here, you could just get rid of the double bond and make that neutral with NaBH3CN. Right? This would just reduce the iminium ion into the amine right there. Yeah. Remove the double bond and the positive charge. Right. That's it. So let's do an example. Okay. Here's a practice reductive elimination problem here. Right. Uh-huh. Oh, predict the product for this reaction. Predict the product. Yeah.
Oh no.
Uh-huh.
I was thinking it's manic, but we don't have a behind.
Oh yeah, that's later. That's later, manic.
Isn't it just like a place where the O is?
Uh-huh. Right.
Yeah, and then it like carries the rest of like
Yeah, that's it. Uh-huh. Because it first goes through this iminium ion first, and then we reduce that iminium ion with the NaBH3CN to get rid of the double bond and the positive charge.
you have to draw in like the H. Where does the H go?
Oh, right. So in this reaction here, one H of the amine always leaves.
The one that H. Yeah.
Oh, this H here is the H of the amine here.
So do we have an H?
Right. Over here, we only had one H. Where that one H leaves, and then there's no more H on that nitrogen. But this amine here had two H's. Right. Yeah, that's a good question. This is a primary amine. This is a secondary amine. This reaction will not work with tertiary amine. This won't work with the tertiary amine because
So this only works with primary and secondary.
and ammonia. Right. Ammonia, primary and secondary amine. Ammonia is like no R groups.
So like, would you say reductive elimination is only for primary?
Uh, ammonia, NH3, primary, secondary, amine. Right. Uh, no reaction. No reaction with tertiary amine. Yeah. So that's reductive amination there. Hoffman. Okay. Let's go over Hoffman. Right. Okay. So for let's say yeah. Oh. Oh, sure. I thought you guys were calling, asking a question or something. Let's see. Okay. Mhm. Okay. So at the beginning of this session, what did we say the first part of Hoffman elimination was here with this first reaction? With that, I mean,
Reduction
so we have an amine here with a pair of electrons, right? And then this uh, over alkylation, right? We're gonna over alkylate this amine with methyl groups because that's what we have as the R group there, right? It doesn't go through here in one step, right? Because what happens first is that this attacks the methyl group and kicks out the iodine, and then this nitrogen with the methyl group will have a positive charge. And how do we neutralize this positive charge here? How can we neutralize the positive charge on the amine? Right, like it first goes through this intermediate here, right? But can we neutralize this positive charge, nitrogen? Yeah, we can deprotonate the nitrogen here. Um, right. So when we deprotonate that, that's gonna have another pair of electrons, right? This pair of let's say K2CO3, right? That's the base that's gonna deprotonate that hydrogen to make this neutral. But we're gonna do this reaction again because we have that pair of electrons right there that can react again. Right. So that's the first part of Hoffman elimination, over alkylation. Okay. Once we have this point right here, what does Hoffman sound like in monoethylene A? Like, what reaction comes to mind when you hear Hoffman? Left subside, right? E2 reaction on the left subside. So we could either, let's say, make a, let's say, the first thing you do is find your beta carbons, right? This is the alpha carbon to that nitrogen, alpha carbon, alpha carbon, alpha carbon. This is the beta carbon, beta carbon, beta carbon. That's the first thing you do. Find the beta carbons, right? And then draw out at least one hydrogen on the beta carbon. So beta hydrogen, beta hydrogen, beta hydrogen, right? If we're trying to make the less stable double bond, the less substituted one, let's say this is beta hydrogen A, B, C. Which beta hydrogen do we want to deprotonate? The C one, right? Because it's the less substituted one. And this is just a form of hydroxide ion. But you're gonna see Ag2O, right? That's gonna deprotonate that beta hydrogen, form a double bond here, and then this makes this whole thing is a leaving group, right? Yeah. So the next thing we want to do is do a Hoffman elimination reaction, which makes the less stable double bond, right? And to do that, find out all the beta carbons and then choose the one that is the least substituted to make the less stable double bond, right? That makes this whole thing the leaving group. Because you know how for elimination reactions, we use like leaving groups like bromine, chlorine, something like that. Imagine that as like a bromine right there. Like this whole dashed structure is a bromine. When we do the elimination reaction, we're gonna create this double bond right here, and then we're gonna have this amine right here, right? But do we stop here with the pair of electrons? No, we could keep reacting it with the methyl iodide, right? Uh-huh. Yeah, plus, because like this right here can get methylated again, right? So let's methylate that again. And then we repeat the whole process again. So alpha, 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 beta, beta, A, B. Which one? Wait, let's do hydrogen. Hydrogen, hydrogen. Which hydrogen do we want to deprotonate to make the Hoffman alkene, the less stable alkene, A or B? Right. So A here is secondary because it's attached to two other carbons, but B here is primary. It's only attached to one other carbon. Yeah, so we want B. Right, we want the less stable one. OH minus will come in, attack, make a double bond there. And then this right here is our leaving group. Right? And when we do that, we get the alkene, the less stable alkene, and then we get this leaving group here. Uh, 1, 2, 3. And then for Helix, he leaves it as the final side product, but it actually goes down further to this over-alkylated amine right here because of that pair of electrons, right? But there are no more beta hydrogens, so we can't make another E2 reaction. We can't make another double bond because there's no more beta carbons, right? If you put this, then that's acceptable, but this is the more correct way because it will over react again with that pair of electrons right there, right? Where this is one of your products and the other products is here, right? So that gives you this plus this plus uh, this. Yeah. Yeah.
When you said like the leaving group leaves, like
Uh-huh.
where, what? But it looks like some parts of it didn't leave.
Oh, for this part here. Oh, the one here.
No, the one in
Oh, this one. Right. So this nitrogen here is going to be this nitrogen right here. That nitrogen is attached to two methyl groups. One, two. Two methyl groups. One, two. This whole thing here. This whole thing is the leaving group. That whole thing, think of it as the bromine. Right. Like this. Yeah. Now we're using the leaving group to react again. Right. This was the leaving group that left. Right. This is the product that formed, but the leaving group that left can react again with the CH3I to get over methylated again. And then we keep going on and on and on until we get to this point here, until we get to the trimethylamine or the over methylated amine. Yeah. Uh-huh. Right.
I guess what's like the point between this one and like the bad method? It's also over.
Right. So the point for this one is just to make alkenes, the less stable alkene. Right. This is just a reaction of the amine. The bad method here was trying to make amines, right? But in this reaction, we are already starting with an amine, and then we're just making less stable double bonds. Less stable double bonds, where we always end at uh, the over alkylated amine, over methylated amine. Yeah.
So, like, if we don't have K2 or A2,
Yeah.
we're not forming double bond. It's like the same kind of like similar question. We just and this would be the answer.
Yeah, that would be the answer. If you have no Ag2O, then you stop at this answer here.
Calculation.
Right, because there are still beta hydrogens because this is alpha, 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 alpha. Wait, no, that's the alpha one right there. Like this is the alpha one, and these are the beta ones right here, right? If you had Ag2O, then you would choose the less substituted one, which is
But
going to be that
since
one.
we don't have A2,
2O.
so we're not creating any alkenes.
Yeah, you're not creating any alkenes because there's no Ag2O there, right? You need this Ag2O to go through the reaction. If there's no Ag2O, then you just stop at here as the final product, right? Uh-huh. Right. Okay. Next one is manic reaction. No, manic. Okay, manic. It's a big one. Wait, what time is it? Okay, 3:17. Yeah. Try to speed this up. So for manic, you're gonna get a lot of reactants. You're gonna get 3 reactants. Right? The nucleophile of the manic is going to be enol. The electrophile of manic is going to be an iminium ion. Right? This enol here will come from a ketone. The iminium ion here is going to come from an aldehyde plus an amine. And the product that you're gonna get is gonna be alpha, beta, alpha, uh, beta, a beta amino carbonyl. And I'm gonna show you an example of this right now, where let's say we have these reagents here, this ketone plus this formaldehyde plus, let's say, uh, this amine, and this is gonna happen in acidic conditions. Like, what are the reagents for manic? Like H. 3 to 5. Acid. This reaction happens in acidic conditions here, right? The aldehyde and amine will form the iminium ion, where this carbonyl carbon of the aldehyde is going to be this carbonyl carbon, not carbonyl, the iminium carbon, like that, right? Where one hydrogen of the amine will leave in the mechanism. It's like the last reaction we did with the reductive amination, where when we put an aldehyde and amine together, we create this iminium ion here, where one hydrogen goes away, right? This one here will be your enol, right? So for here, this iminium carbon here is the electrophile, that dot carbon right there. The nucleophilic atom is going to be this alpha carbon of the enol right here. That's the nucleophile atom right there, the alpha carbon of the enol, right? So you could just think of it like this: the alpha carbon of the ketone there is the nucleophile right there. When we combine these two together, this is what we get, right? This is the star atom, the nucleophile. This is the new bond, which is the star and dot atom. This dot atom is attached to 2 hydrogens, and you can leave that as invisible or draw them out. And then this amine right here, right, where we get rid of that double bond and positive charge to make that neutral, right? And this right here is a beta amino carbonyl, because this is the alpha carbon of the carbonyl. This is the beta carbon of the carbonyl, and on the beta carbon we see an amino group.
Also, like in a way, like
Extending the chain, yes, it's combining multiple components into one component, right? And I'll teach you the retrosynthesis of that, like how to go backwards for synthesis. Like if you see a beta carbonyl, amino carbonyl, what cuts to make to go backwards, right? Because from here, here's the disconnection for retrosynthesis, right? So the first thing you do to go backwards is you cut the bond between the alpha and beta carbon, and then the alpha carbon is going to be coming from the enol or ketone, and then the beta carbon is the iminium ion carbon, right? We got one of the components already for manic. There are three components. Um, to get the other two components, we got to cut up the iminium ion, right? So the next disconnection you do is cut the carbon double bond nitrogen, right? Where the carbon is the aldehyde carbon. The nitrogen is the amine nitrogen. So let's do an example of that. Let's say we have something like this. Right? So the first thing you do, if you have this as your synthesis product, and then you try to react the reactants that came from fermanic, find the alpha and beta carbons to the carbonyl. This is the alpha carbon, that's the beta carbon, right there. Then you cut the bond between the alpha and beta carbon like that, right? Once you make that cut right there, this arrow here is going backwards. This is what you get right here. Where we said the alpha carbon was the enol carbon of the ketone, and the beta carbon is the iminium ion carbon, which is that iminium ion carbon right there for the beta carbon, right? Now the next cut you make is going to be between the iminium carbon and the nitrogen right there, right? Where there's going to be an aldehyde on that iminium carbon. So let's go backwards one more time. Where this is the aldehyde, and then the amine is that right there. Where I added a hydrogen right there because for this reaction, manic reaction, one hydrogen of the amine always leaves, right? But when we go backwards, we add the hydrogen there. So this, where did which O come from? Oh, this O right here. Yeah. So this O came from the aldehyde right here because you know how for the reaction, the amine always reacts with the aldehyde to create this iminium ion here. So that's how we go backwards. This is an intramolecular manic, or partially, because the first step here is to form the iminium ion, which was the intermolecular reaction, right? Like they're separate. But then when we react the enol with the iminium ion, that's the intramolecular reaction. Because the enol is on the same molecule as the iminium ion, which forms a ring right there. So that part is the intramolecular part. The first part to form the iminium is the intermolecular part, right? This overall thing can be all intramolecular. Do you want to try to see an example like where everything is intramolecular? Yeah, let's do that. Let's do that. Let's see. Okay, let's do that. Okay. So if I try to make this all, uh, let's say alpha, beta, and then this is the amino group. Okay, so here's another beta amino carbonyl because at the beta carbon we see an amino group right there. Same first step, make that cut between the alpha and beta carbon, go backwards. Where what was this carbon right here? Like the beta carbon after we make that cut. Yeah, the double bond iminium thing. right? Now, the next cut we make is between that carbonyl, that iminium carbon and the nitrogen to get the aldehyde because we know that used to be the aldehyde right there. And then I added an extra hydrogen on the nitrogen right there, where this is an all intermolecular manic reaction. The first thing that happens is form the iminium ion between the aldehyde and the amine, and then the next thing react the enol with the iminium ion. This is the reactant that made this right here. Right. Yeah. Um, let's do practice for manic where they give you the reactants like the ketone, aldehyde, and amine, and then predicting how the product would look like. Okay, let's do that. Okay, let's do that. Let's say we have something like this. Right. Where let's say we have okay. So if you see something like this on the exam where we have three components: a ketone, an aldehyde, and the amine. The first thing I do is find the aldehyde and amine to create the iminium ion, right? Where this is the aldehyde, this is the amine. When we combine those two together, we are going to create. Wait, actually, I'm just gonna teach you guys how to go directly to the answer without doing all this stuff in the middle, right? Like so it's way faster. It saves time. Okay, so for the ketone, find the alpha carbon. Doesn't matter which one because it's symmetrical. Star that. Find the carbon of the aldehyde. Dot that. Make the new bond between the star and dot. So let's say we have uh, this ketone here. New bond between star and dot. Right, that's the new bond between them. This dot here is attached to a phenyl group, right? And then that dot right there is going to be attached to the nitrogen right here, right? Let's say this is a circle, circle, right? Yeah. So that's how you can go to the manic reaction product right away from these three components, right? Star dot circle, and then that's the star dot circle connection right there. Yeah. Okay. Okay. Last two reactions of the amine chapter: nitrosation uh, with the Sandmeyer reaction and phenol stuff. Okay. And then to confirm if you have the right product or not for manic reaction, right? Always make sure you have a beta aminocarbonyl. So if we try to predict this as a product, we gotta make sure that at the beta carbon there's an amino group right there, which checks out beta aminocarbonyl. Okay, next rotation. Okay, this one is fast. Let's say from a primary amine, you're gonna create a diazonium salt like that, or you can say it as wait, or this as the where this is the N2 right here with the positive charge, and then the chlorine here will have a negative charge. There's an ionic bond between the positive and negative charge here, right? For the secondary amine, we're gonna have like that. Oh wait, this is still a primary amine. Yeah, yeah. This is still a primary amine. This is a secondary carbon. Wait, here's the secondary amine. There you go. Yeah, there you go. Yeah, nice, nice. No. I was wrong. I was thinking about the carbon. Like I made a primary carbon, secondary carbon, tertiary carbon. This is also a primary amine right here. Oh my gosh. Right. Tertiary amine here. Oh my god, that was let's see. So we have that, that, and that's it for those reactions. Where the primary amine part right here, this would be Sandmeyer reactions, like the copper X, where X could be CN, Br, chlorine. That's the next chapter. This reaction comes back at that chapter with the benzene stuff. Yeah. Hydrogenation, bridge reduction, very vinegar. Okay. I think. Okay, let's speed run the last chapter for this one. Okay, let's go. Now, synthetic radical halogenation. I'm just gonna write out this names. So right now we're on phenols. We just finished the first chapter on the means. We're gonna go on the benzenes one. Let's say we have a benzene like this. 118A reaction, free radical halogenation, X2, like Br2, and light or heat, right? This would add a halogen on the carbon that gives us the most stable radical. And in this case, the carbon that will give us the most stable radical is going to be this benzylic position here. This carbon is benzylic. And a lot of these reactions will react with that benzylic carbon right there, right? So that's why we're going to add the bromine on that carbon here. Right, so that's that for benzylic radical halogenation. Benzylic SN1. let's say for this one, you have water, ROH, OH, OR. So this is going to be an SN1 reaction here, where the very first step of SN1 reaction is that the leaving group leaves first to form a carbocation here, right? And then from that carbocation, if you could use two different kind of nucleophiles here. If you use water, water is going to create an alcohol. If you use an alcohol as a nucleophile, you're going to create an ether, where the R group of the ether depends on the R group of the alcohol, right there. Yeah. Oh yeah, yeah. So this is just a short way to say the benzene ring. Uh-huh. Oh, I am. Right. Yeah, that carbon right there. Yeah. Yeah. Uh-huh. Yeah. Uh-huh. Okay. Now let's go over oxidation. So I'm gonna go over this one like this, right? And then let's say we have KMNO4, uh, KMNO4, water, heat. What reaction would this do here? With the KMNO4 and yeah, which ones? Which ones? The- oh, yeah, all the benzylic hydrogens, all the carbons has a benzylic hydrogen. So this one right here would be no reaction because there's no hydrogen on this carbon right here, right? Where every other thing would become carboxylic acids. No, nothing happens to that butyl right there, right? Now, how about this one? Okay, what would this reaction do with manganese oxide? Benzylic position, right? This oxidizes. Yeah, not alpha or benzylic or allylic alcohol. So no reaction because here because there's no like that carbon is not benzylic. No reaction here because this alcohol is not benzylic as well. This one is the only one that reacts because this carbon here is benzylic to that benzene. Right. So that's the reaction there. Okay. Keep going. The final material, yeah, it's not that much. It's short. Yeah. Let's see. Hydrogenolysis of benzyl ethers. So let's say we have something like this, right? Versus something like this, and then we do H2PDC, H2PDC. This reducing agent here will only reduce benzylic ethers, right? Which one of these are benzylic? Right, the first one, because this benzylic carbon here has the OR group. This benzylic carbon here does not have an OR group, right? This is still an ether, but this carbon is not benzylic, that carbon is not benzylic. So what you gotta do to predict this is make a cut between them where you're gonna get a toluene and an alcohol, right? For this one, no reaction. So this is used as a protecting group for alcohols, right? Because let's say we have this kind of synthesis problem where we have an alcohol and then we want to do this, right? So you see how here for this synthesis problem here, we want to do a Grignard reagent on that carbon to carbon, right? Like this is the RMGBR that would attack that carbon and pop that up there and protonate that, right? But the Grignard reagent will actually deprotonate the alcohol instead because there is a hydrogen here. And Grignard reagents will act as a base first over a nucleophile, right? So we can't do Grignard right away. We first got to protect this alcohol. So to do that, we got to do NaH to deprotonate that alcohol hydrogen, and then do this reagent here, Br, to create the benzylic ether. So that's going to create us um, like that, and then my gosh, there we go. Oh no, there we go. And then uh, and then we could do the Grignard with that MGBR, H plus workup, and here, right? Where H2PDC will reduce this benzylic ether into the alcohol. It would not react with the alcohol here, this other alcohol. Yeah. Uh-huh. Mm. Yeah, we're protecting the OH from this Grignard here because we can't do the Grignard right away because this Grignard here is a strong base and nucleophile. Acid-base reactions are one of the fastest reactions in OChem, so this would actually deprotonate the alcohol hydrogen instead of attacking the carbon there. Oh, you're thinking of this here. You're thinking of this Grignard reacting with carbon dioxide, right? And then that would with H plus workup. Yeah, CO2 for the carboxylic acid. This is not a CO2, it's just a ketone. Right? If it reacts with the CO2, then that would be carboxylic acid. Yeah. Um, double one O. Double one O. Oh, this double one O here? Right. So this double one O is the electrophilic carbon that Grignard here attacks that carbon to carbon, pops the double bonds to oxygen to become O minus. O minus gets protonated by H plus. Workup. Right? Because this Grignard reagent here, the atom attached to the Mg is partially negative. This carbon to carbon is partially positive. Nucleophile attack electrophile, pop the double bond to the oxygen. Oxygen with the negative charge will get protonated by the acid workup to become OH. This is the new R group of the Grignard there. Yeah.
The mechanism of Grignard plus CO2
Uh-huh.
is this? Like, would be of this reaction, if you do the mechanism, that would be that. Because he emphasized yesterday that the one with CO2 you get a carboxylic acid.
Right. This you would get first, and then to get to the carboxylic acid, H3O plus or H2SO4. Yeah.
Can I take a photo?
Yeah. Uh, yeah. Grignard reagent plus carbon dioxide. Carboxylate and then followed up by acid workup, carboxylic acid. Yeah, that's one of the methods to add an extra carbon and a carboxylic acid. That's one of the methods. Do you remember the other method that can add an extra carbon and make a carboxylic acid as well?
Do we just go over NCN and then H2SO4?
Yeah, right. NaCN and then hydrolysis of that nitrile into the carboxylic acid by H2SO4 water and heat. Right, right. And there's limitations for both, right? Because for the Grignard one, we can't do that in alcohol solutions like this, right? We gotta protect it first, but that's extra step. For the NaCN and the H2SO4 route, since that's using acidic conditions, we can't do that in alkenes. Like if there's an alkene in the reactant, we can't do that. And that showed up on the first midterm. Like there was an alkene on the reactant, and then some people chose NaCN, but that didn't work because the alkene will react with the acidic conditions instead, right? So you gotta do the Grignard and MGBR route with the alkene in there. But if there was an alcohol there, you gotta use the NaCN route or protect the alcohol first, right? Uh huh. Yeah. Okay, move on. So next one. Okay. Uh, Birch. The reaction?
Yeah, as before.
Yeah, right now I'm on
Oh shit.
Birch. We gotta go through all this.
OMG.
I know. So we're probably not gonna get over midterm 3, but we could go over midterm 3 on Thursday. Yeah, unless you guys want to do new material first and then midterm 3 on Thursday. New material.
After the new materials.
Yeah. Oh, this is taking longer than expected. Like I planned to do this in like 1 hour, but I know so much stuff. Yeah. Yeah.
Is this
Uh-huh.
question related to what we did before?
Oh, this is from winter 1 material. It's not gonna be related to this midterm here. So it does have to be H2SO4 and water. You can also see base NaOH, where we have an ester here. The ester is gonna get hydrolyzed into the carboxylic acid here, and then make the alcohol right there. Like that's
What I did was I just
the
did
alcohol.
this
Uh-huh.
and I just put hydrogen here.
Yeah, hydrogen on the oxygen. That's right. That's right.
Wait, so oh no, no, I didn't put
Oh, you didn't put the
OH.
O there? Oh, I see. The O is still going to be there because you're going to make that cut between the carbonyl carbon and the oxygen right there. And then when you make that cut, that's the alcohol
Oh,
group.
it's like the same question in which we have a ring. If we open the ring, one makes carboxylic acid, one makes OH.
Oh, wait. Yeah, yeah, yeah. Uh-huh. Say. Uh-huh. Birch reduction. So this is going to be like if you have a benzene like this. Um, this is going to be I forgot. Sodium and something. Right, but that's gonna give you this. Right, do you guys remember this kind of product? The Birch one, yeah, with the EDG and EWG on it. This sodium is something else. Oh, NH3. Yeah, something like that.
And then L something.
And then yeah.
There's also one other thing. I don't know if you can read it.
Oh yeah. And ethanol, ethanol. Yeah. I got it. I got it. Right. So this is the simplest case here with no EDG, no EWG. But if you have an EDG on it, wait, first, it goes through this intermediate right here. This is important to know, right? Where the carbons that are sp3 hybridized will have a radical and a pair of electrons, right? Like the ones that are sp3, oh not sp3, but the ones that are not double bonded. The ones that are not double bonded will have a radical and a negative charge there. So let's look at the EDG example. Like let's say we have OCH3, same reagents, OCH3. Right. So if this is an EDG right here, do we want a negative charge near a negative charge? Is that stable? No, right. So we want the double bonds to be attached to the EDG, right? Because the ones in between here have the negative charges, right? So that's it for the EDG. For EWG, like let's say we have NO2. This is gonna stabilize a positive charge or a negative charge, right? Which we do want a negative charge there. To put that negative charge there, the double bond's gonna be like that, right there. Because in the intermediate right there, the negative charges are right there, right? This could get tricky if there's multiple groups, right? So let's say we have something like this. Okay, and then we also want the Okay, where would be your two double bonds in that product here? This one? This one? Right. So to tell if something is an EDG or EWG, right? Look at the very first atom. If it has a partial negative charge, it's an EDG. If it has a partial positive charge, it's an EWG. This is negative. This is an R group, and R groups are also EDG. This is EDG. This nitrogen here is partial negative, so this is EDG. This carbon to carbon here, the charge of that is partial positive, which is an EWG, right? So EDG, 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 EWG. Yeah, because the negative charges here are avoiding the EDGs and they're stabilized by the EWG, right? So that's how you do that one. Uh, yeah, right. You don't look at this carbon here, right? Because this carbon is partial positive, but this is not an EWG because it's not the first atom attached to the system here. We only look at the very first atom attached to the system, and that's the only thing we care about.
On a cheat sheet, we see that by electron joining group does touch, electron withdrawing into the
Yeah, electron donating group touches double bond. Electron withdrawing group does not touch double bond. That's another way to think about it. And the reasoning is because of the negative charges in between them, right? We want the EWG to stabilize the negative charges, and we want to avoid the negative charges touching the EDG or near the EDG. Yeah. Right. Okay. So I have 5 minutes left for my shift. Which reaction do you guys want to go over for this last chapter? All of the above. Kobe, Kobe Schmidt, the hardest
Which
one.
one do you think would be like very apparent to be on the final?
Sandmeyer.
Okay. No, we didn't.
Let's go over
said all the red ones are important.
all the red ones. Okay, we did that. We did that. We did all those stuff already.
In the parentheses, he said they're not
Might show up in
relevant.
synthesis. So this one is more for synthesis, and also Sandmeyer. Yeah.
Oh, what is? Did we just did this?
No, this is the Sandmeyer
Oh, he
one.
said this could be on because
Yeah,
he
yeah.
said these two we
Uh-huh.
didn't cover. These are not
Oh, yeah.
percent.
He said
these will
Be on the
might
final,
appear.
right?
He
The
said
Kleisen
they
and
might-
Cope. Right, let's go over that. Kleisen and Cope. Yeah. Okay. Right. So for Kleisen rearrangement, you're gonna have an allele vinyl ether. For couple rearrangement, you're gonna have a 1, 2, 3, 4, 5, 1, 5 dying. Okay. So let's say we have right. So for Kleisen, these like rearrangement ones, right? Kleisen, you're gonna have an allyl vinyl ether, where this is the vinyl carbon. The carbon on the alkene, the carbon that's part of the alkene, right? So this is the alkene right here. That carbon is part of the alkene, so that's vinyl. This is the allyl carbon because that's the one carbon alpha to the alkene. one carbon away from the alkene, right? This is the vinyl carbon. This is the allele carbon. Allele is one carbon away from an alkene, or alpha to an alkene. Right? Allele is one carbon. Vinyl is that. So vinyl ether, allele ether, because at the allele carbon we have an ether as well. Yeah. Yeah, you need both vinyl and allele. Yeah, ether for Claisen rearrangement. Right. And then here's the arrows. Like that. And that's the final answer. Right? Yeah, that's the mechanism. That's the mechanism. Right. And then for the cope rearrangement, there are no oxygens. Right. It's a 1,5 diene. So let's say this is 1, 2, 3, 4, 5, 1,5 diene. Um, well, these are not rings. Like they're linear chains, open chains. Well, don't think of it as rings. Think of it as allele vinyl ether, like this, right? Because he could give you it in this form right here. He could give you it like and then you just gotta rotate it into this template right here. But I could do that rotation thing after that, right? And for this one, you can see like 1, 2, 3, 4, 1, 2, 3, 4, 5. Like that. Heat, right? You can see in this form as well for coat. Yeah. So this one, and that's the answer for that. Yeah. For Claisen rearrangement, we're always making the bond between the allele carbon and the oxygen right there. We're always making that bond. Yeah.
And this only happens with isolated, right? Isolated conjugation.
Isolated conjugation. Yes, isolated conjugation. Right, right. This has to be isolated because if this was conjugated, like this double bond was here instead, then this is gonna be very stable, unreactive. It won't react. Yeah. Yeah. Isolated, meaning that this alkene here and this alkene has to be isolated. If this was like closer to this benzene ring right there and it's actually conjugated, does that make it more or less stable? More stable. Is that less or more reactive? Less reactive, which is why it won't happen in conjugated alkenes, right? So just practice with that, and then let me know how it goes. The bottom over here is gonna be the exact same question over here, but given in this form that you might see on the exam.
Oh, I thought that's what we get from plus to the second.
Oh no. These are two different questions. Yeah. The three tetra thing. Oh, this thing here. Oh, that's part of the problem.
But where is it on the top part?
Oh no, these are separate. These are separate. These are practice problems.
They're not those.
No, they're not those. Yeah, this is the product for that. This is the product for that. This is just practice problems that you might see on the exam, the actual exam. Yeah.
You guys have ours tomorrow, right? It's Tuesday.
Yeah, I'll have it tomorrow. But I'll have it on Thursday, and then I know we didn't get over for midterm 3. So on Thursday, do you want to go over the new material or midterm 3? Like which one? The new material.
That's short.
Yeah.
Yeah.
Yeah. Because midterm 3 was the sugars stuff, the Claisen rearrange, the Claisen condensation
Because we're
stuff.
missing more of the new stuff.
Yeah. Uh huh.